What's up, kids? This is Mr. Carlson, C-Squared Mathematics. Welcome back to Algebra 2.1. We are now in Unit 3, which is just quadratics. So during quadratics, we're going to do a number of things. So this week, we're going to be reviewing factoring. I know we sort of did a lot of factoring throughout the quarter already, but this week, we're specifically going to go into different types of factoring, maybe some new factoring models, and as well as review some old factoring, and then how it applies to equations. How can we solve quadratic equations? How can we find what x equals if I'm given a quadratic function? That's this week. Next week is going to be primarily on graphs. How can I graph quadratic equations? We're going to spend 2 days on that, Algebra 2.1 style, and then we're also going to be going through our very last lesson of the whole quarter next week, and that is writing quadratic equations. If I'm given a graph, how can I write quadratic equations? Okay, so I want to go through some bell work. That's going to be over the Unit 2 test, which you should have taken already last week. Retakes are available this week. Going to go through the objective essential question, the actual lesson factoring review, and then, of course, summary, closure, and so forth. Okay, I have a lot of questions for the bell work, so you'll see up here when you get on the PowerPoint that you'll be able to click on each individual titles. So if you don't want to go through these questions, just kind of go back to the PowerPoint, click on the questions that you want to actually go through, and I will actually that link will take you to where I actually go through that slide. Okay, so pause the video if you need to, so you can write this down. I'm going to get started right away. So this is rational exponents. First things first, in order to solve this equation, I could technically solve this on Desmos, by the way. Very technically, I could. I'm not going to do that right now. But how do I solve this? Well, the first thing I need to do when I solve this is equal it to 0. Or before I even do that, because I know I have to equal it to 0 eventually because this is a quadratic. Before I do that, I need to isolate this part. So this part is the actual rational exponent part. I need to isolate that. If I don't isolate it, then no bueno. I can't do anything. So, bueno means add the 13. Okay, so you add the 13 so I can isolate this part. So now what I have is in parentheses x squared minus x minus 29 all to the power of 3/4, and then equals, when I add 13 to there, I get 27. Now when I get to this part, I notice that the left side is actually isolated. That's what I want. That's good news. That is bueno, all right? Now what do? Well, I take this whole thing and I technically take it to the reciprocal power. So to the 4/3 power. If my exponent is 3/4, I need to take it to the reciprocal, flip that exponent, and do the fractional exponent and do 4/3. But what I do to one side, I must do to the other. Those go poofy. Now what I'm left with is x squared minus x minus 29, and then equals, what the junk is this? Okay. What the junk is this is, there's a couple of ways you can write it. I'm going to write it like this. It's the cube root of 27 and then to the 4th power. That's one way to write that, okay? So my denominator here, that 3 is the index, and then the 4 is my exponent of the whole thing. So I can rewrite that as a radical. You can also plug this into Desmos, just the right side, and you could definitely get an answer that way. But essentially what that equals, cube root of 27 is just cubed, and then to the 4th power, and that equals 81. Okay, so far what I have is all this junk. Okay, now I can equal it to 0. So what I want to do is subtract that 81 over. I have x squared minus x. Negative 29 minus 81 will actually give me negative 110, and this equals 0. Now, when I get to this step, I'm going to finish the work up here. When I get to this step, I need to factor it. So what are factors? Things that multiply together. And this is great. We're going to be doing factoring review today. So what are factors? Things that multiply together somehow, some way that give me negative 1, this negative 1x here. That's the coefficient. Well, it should be pretty obvious. 11 and 10. If I times 11 with 10, 11 times 10, I get 110, but when I somehow add them or subtract them, I get -1. So I have my basic template here equals 0. And then I'm going to add in these parentheses my factors. So this is 11 and this is 10. But which one gets a negative and which one gets a positive? Okay, I know it needs to be one needs to be negative because this is -110. So that means 11 times 10 gives me positive 110, but 11 or 10, if I add a negative to either one, I get -110. Now I look at this is a -1, so I need to make sure when I add these two numbers together, I will get -1. So if I put the negative with the 10, 11 minus 10, does that give me -1? 11 minus 10? No. So I need to put the negative with the 11 because the -11 plus 10 gives me -1. But -11 times 10 gives me -110. So now what I have is this. So what does that equal? This will equal two numbers, positive 11 and then -10. So I set each of, I didn't show that step, but I set each of these equal to 0. That's what I did there. Okay? And then, of course, I just solved for x. Fantastic. You would originally check these, but it does work out, so you don't need to check them. Okay, this one. Let's go to town on this. So this one is a little bit tricky because when I do the reciprocal, it is isolated, so I have to do the reciprocal right away. That goes poofy. I'm left with x minus 2 equals. And then this is actually the square root of 100, and then it's actually cubed, okay? The square root. Now this is technically a 2 here for my index, but we don't even write that at all. Now the problem with this is, and a lot of you miss this on a test, is that this is a square root. So right here, this is a cube root. There's really only 3, all right? But this is a square root, which means I don't just get 10, I get plus or minus 10. And that's very important. And then I take that to the third power. Of course, I still have x minus 2. So I have two answers here. This is plus or minus 10 to the third power is 300. This is x minus 2. So my two answers are actually as follows. X minus 2 equals positive 300. And then x minus 2 equals negative 300. So that means when I add the two over, I get x equals 302 for one example, or one solution. This is primarily what most of you got, that answer. But the other answer you forgot to do, or primarily had, sorry, that's what you primarily had. But the answer that you primarily forgot was this negative version. So if I add then the two over, I get negative 298. Okay, so I get negative 298. So x equals both these answers. X equals 302 and x equals negative 298. Okay, that was a kind of a tricky question there, but I remember going through it on the video and I told you that this would be on the test. So hopefully you paid attention. Let's erase that and move on. So this is the next one I have. Just rational exponents again, and all we want to do is simplify the expression. No equations involved here. So I notice that this is a power to a power. This is 2. But also notice that this 5 does have an exponent of 1 right there. It's just hidden. What does this mean? This means that this 2 goes to that exponent of 1 and to the 1/3. So far I have 5 to the first power to the second power times y to the 1/3 power to the second power. That's what that means. And of course, y to the 1/6. Okay? So when I start simplifying this, well, I multiply these. This is truly a power to a power. So if I take a power to a power, what that equals is multiplication. Wow, that looks awful. Did you see that? I saw that junk. Okay, what it means is multiplication. Okay, so I take those two, multiply them together. I take these two and multiply them together. I multiply the exponents. So 1 times 2 is of course just 2. And then this would just be y to the 2/3. 1/3 times 2, 1/3 times 2 just gives me 2/3. Okay? And this is all over y to the 1/6. Okay, what does this equal? Well, this is going to be 25, and then this is y to the third 2/3 all over y to the 1/6. Now, when I get to this part, I notice two things. I notice A, I have a fraction, and B, these both have a base of y, which means I can actually simplify those. But I simplify this by looking at my exponent. So now instead of multiplying, when I have the same base but their division, I actually subtract these exponents here. So let's put a note here. And I'm going to take 2/3 minus 1/6 because that's what I'm going to do. 2/3 minus 1/6. How do I simplify this? Well, I need to get common denominators here for my exponents. My common denominator is 6. That's my least common denominator. How do I get 3 to 6? Well, times 2 gives me 6. What do I do to the denominator? I do to the top. Times 2 gives me 4. So this means 4 minus 1 is 3 all over 6, which is 1/2. So this right here is not my answer, but it is my new exponent. So now what I have is 25 to the y, or 25 times y to the 1/2 power. This is my final answer. You can also write it as 25 times radical y. You can also write it that way. Okay? Tricky just because of the exponents there. Let's erase and move on. I know we're going to town, but they're good towns. All right, this one. This one is a little bit tricky just because you have to break it apart, like consistently always. So I am going to break this apart into each individual radical with cube roots. So times the cube root of x, and then times the cube root of y cubed, minus y times the cube root of 54 times the cube root of x. That's what I would normally do. I would break that apart so you can see everything very, very clearly. So now the cube root of 16, we can break this down to be 4 and 4. This is 2 and 2, 2 and 2. Okay, and then we can also see right here, this y to the third, those go poofy because they're inverse properties. So the y to the third and then the cube root, they go poofy. So I'm just left with y. So what I'm going to do is I'm going to do something really just quick here. I'm going to move this y out front because that y does come out front of the radical. It's done. It's just y. Those went poofy. Now the 16s, remember, since it's cube root, I have to circle 2 or 3 of these 2's. And since there is a set of 3 right here of 2's, that means that comes outside as well. And it gets tagged onto the y. But what's left? There is a random 2 just chilling in here. And so this is times the cube root of 2. But there's also this. Can that simplify into anything? No, it can't. So that means that's also a cube root. So I'm actually going to tag that x underneath the radical. I can do that interchangeably. I can put it in, take it out, and separate it, but still, no matter what, underneath my radical, my cube root. So that's the left side. Let's look at the right side here. For 54, when I have 54, this is a variety of ways I can break this down. The first thing I'm thinking of is 6 and 9. And so this is 3 and 2, and this is 3 and 3. Now notice I do have sets of 3 here. I have one set of 3's, okay? One set of 3's, okay? So that means these I can take out. And so this is 3, right? And then this can't do anything. So this is just times the cube root of x still. Okay, still. Oh, sorry. No. Let me kind of erase this. I still can't do anything with that, but notice something I forgot. Let me put it in purple. I forgot that there's a 2 just chilling in here. What does that mean? That means there's a cube root of 2 that I can't simplify. Okay, so that means that is the cube root of 2. But I still also have this, which means I just tag on that x. So it seems a little bit complicated. It can be, yes. And so that's why we have to do practice over and over and over again so that we can get familiar with breaking this apart. Okay? Now, there's one last thing I need to tag onto this right side. I'm missing a couple things here. First of all, I'm missing a negative between the terms. And second of all, I'm missing this y. This y is chilling out front. I haven't even put that in yet, so I need to put that y there. Okay? It looks kind of confusing with all the arrows. I understand. So just replay the video and try your best. I'm explaining it adequately, I believe. So hopefully you'll be able to get it. We'll see. So now what I have is 2y times the cube root of 2x minus, I know there's a big space here, but minus 3y times the cube root of 2x. Now notice one thing, and then we're going to be done with this question, that they both have a y and a cube root of 2x. They both terms have a y and a cube root of 2x. Which means, since those are technically, they're the same, I can actually subtract them. Okay, I can actually subtract them. I can look at just my coefficients, 2 and 3, and I can subtract them. So what's 2 minus 3? Well, that's going to be a negative 1. And what's my variable technically? My variable is just the y times the cube root of 2x. Perfect. Okay? Awesome. So that is my final answer there. Let's move on to the next one. So this is dividing the complex numbers. You have to do this using what we call the complex conjugate. What is that? It's when you multiply the bottom by what we call the conjugate. The conjugate is really just changing the sign of that imaginary term. That's all it is. You're changing the sign of that imaginary term. But what you do to the bottom, you must do to the top. So that's what we call the complex conjugate. So I'm going to do my complex numbers. So the complex conjugate. Very interesting. Okay, so now when I multiply all this, we're going to FOIL it out. And so 7 times 6 is 42. 7 times negative 5 is a negative, I didn't even put 2 down, is a negative 35. So 42 minus a negative 35i, imaginary numbers. The inside terms, that's going to be plus 48i. And then right here, that's going to be negative 40i squared. Because I times I is I squared. 5 times negative 5 is, or 8 times negative 5 is negative 40. This is all over something. So what is that something? Well, this something, since I multiplied by the conjugate, the reason why I did that is so I can eliminate the imaginary numbers from the denominator. I don't want imaginary numbers in the denominator. You can't have imaginary numbers in the denominator, which means this is why I'm doing this route. So when I do that, when I multiply by what we call the complex conjugate, what happens is the middle two terms of FOIL, if I had 4 terms, which I have here, this is your F, your outer, your inner, and your last. That's what FOIL is. So your middle 2 terms, your outer and your inner, when you multiply by the conjugate here, and when I FOIL it out, what happens is your outer and inner terms go poofy, and you're just left with your first and last terms, which means all I have to do is multiply the first terms and the last terms. That is it. So first terms, 6 times 6 is 36. And my last terms, 5 times 5, with a negative is negative 25, but I times I is I squared. The other 2 terms will go poofy. This, if you don't believe me, this would be your outer term. This would be negative 30i, and then your inner term would be plus 30i, 5i times 6. They would go poofy just like what I said here. That's the purpose of doing the conjugate. So let's simplify this. The top I can actually simplify. So let's do 42. 35 minus 48, or minus 35 plus 48. Negative 35 plus 48. That's going to be 13. Okay, so this is minus, plus 13i. So far, so good. And then I have this, but remember, an I squared is actually a negative 1. And down here, I also have an I squared, so that is also negative 1, which means I have negative 1 times negative 40, which gives me positive 40 instead of a negative 40. And then all over, I have 36. This will be a negative 1. So negative 1 times negative 25 is a positive 25. As we start simplifying, those can combine in the numerator. So this is 82 plus 13i. This is all over 36 plus 25. 36 plus 25, that's going to be 51, 61. So it's going to be 61. Yeah. I guess I'm not feeling it today. So 61. And then I can actually break this apart. This one's kind of really nasty, but I can break this apart to be as follows. So 82 all over 61, and then plus 13i all over 61. Okay, I can break this apart, and the reason why I want to break that as apart is so that it follows the a plus bi form. Okay, and this is actually my final answer. That's why I'm going to box it there. So this is actually my final answer. I don't believe 61 and 82 can simplify. So, yeah. Okay, sweet. So that is how you do that question. Let's erase and let's move on to some of our last belt questions. So here, the reason why this one is difficult is because it has two radicals, but don't worry, you can still solve it normally. You just have to simplify it a little bit. It's a longer simplification. Let's move my pretty face up here. So the reason why I'm going to move that one is so I can make them positive, and so I can isolate this one on the left side. So this is 1 plus and then radical x minus 2. When I do this, what happens now is I can square both sides. But when I do square the right side, I have to take everything. So now that goes poofy, and so I'm left with x plus 7 equals. Squared means double, so I have this. So x minus 2, and then I have 1 plus radical x minus 2. I'm just going to keep this left side just chilling for now. I'm actually going to FOIL this out. Let's FOIL this beast. 1 times 1 is 1. 1 times this is just plus radical x minus 2. Same thing for my middle terms. That's just chilling. And then right here, what I have is just a simple radical problem. It looks pretty difficult, but what if I take radical 5 times radical 5? You guys would say that's radical 25, which would tell me, okay, that this is just 5. If I take radical 3 times radical 3, it's just radical 9, which is 3. In a similar way, when I take radical x minus 2 times radical x minus 2, what really happens, guys, is this. I have a radical and then x minus 2 squared. That's what's really happening. This right here is the same thing as radical 5 squared. But those go poofy, and that's why 5 is your answer. Okay? But those go poofy, which means my answer is just plus x minus 2. Okay? Just my base there. If I have the same radical with the same index with the same base, it's just my base. Okay, and of course, this gets dropped down to be plus 7. Now, a lot of things can happen here, so I'm going to start simplifying stuff out. You ready? I have x's on both sides that go poofy. Those go poofy. I have negative 2 and a 1 right here, which gives me a negative 1. And I have one of these, and I have one of these. Since I have one of those and one of those, 1 plus 1 is 2, so I have 2 of those. So 2 of those things. And then 7, of course. Now what we're trying to do is actually isolate the radical again, which means I have to add the 1 over. I'm going to start it over here or finish it. So that's 8 equals, this is 2 times radical x minus 2, divide by 2. Notice how I'm trying to isolate this radical part. That's 4 x minus 2. And now what I have is a clear example where I can actually take this and square both sides. So that becomes 16 equals, and those finally go poofy. So it takes a long time, it takes a while, but it's there. And then, of course, I can add the 2 over, so x equals 18. Okay, x equals 18. Perfect. Fantastic. Okay, so I believe that is my answer, but let's just check it. It could be no solution, and with radicals, we always need to check it. So this is 18, and then plus 7, not 17, whoops. So plus 7. And then minus, I have a radical, 18 minus 2 equals 1. That becomes 25. And then this is minus, this becomes radical 16 equals 1. So this is 5 minus 4 equals 1, which equals 1. Perfect. So this is actually my answer. This is true. Perfect. It checks out. Fantastic. That doesn't make sense? Email me, let me know, and we'll go through it together. Okay, so that was all my, whoops. That was all my bell work questions. I know I went through those pretty fast, okay, but that's all right. So now we can actually get into the lesson, and because it's factoring review, I will go moderately fast, okay, because a lot of it is some things we've already done before. I will introduce some other things that we haven't done before, but the majority of this stuff we have done before, okay? So I am going to go pretty quick on these. So I can understand quadratic expressions because now it's quadratics, and now we're going to be actually looking at quadratic expressions, and we're going to understand them by factoring. And the essential question is, how do I factor various algebraic expressions? I'm going to show you how. Let's go to town. First things first is GCF factoring. This is the easiest amount of factoring. It's probably the factoring you first learned when you learn how to factor. It is by far the easiest and the most simple. What the greatest common factor, when I want to factor out the greatest common factor, that means I'm going to look at each individual term and I'm going to take out what is common in each of those terms. Specifically, what's the common factor? More specifically, what's the biggest common factor? Okay, so the biggest common factor I see here is 3x squared. Now, the reason why my greatest common factor here is 3x squared is because each one is divisible by 3x squared. That's why. Each one can be divided by 3x squared perfectly. Okay? Because 3 is divided by 3, 15 is divided by 3, 21 is divided by 3, and you get a number. And you can take x to the fourth divided by x squared, x to the third divided by x squared, x squared. Okay? So what this happens is when I take out 3x squared, what I'm going to get are 3 spots left in these parentheses. Why? Because I have 3 terms, right? I have 3 terms here, which means I have 3 spots left. Okay, I take that out. I'm basically reverse distributing. Think of it like that. I'm reverse distributing. So if I distribute that greatest common factor back in, what would happen is I would get this back out. So let's divide these. That goes poofy. What's x to the fourth divided by x squared? Well, I know how to divide fractions. All I have to do is just subtract them. Okay, so I subtract the 2 here. That's all I have to look at. So what's 4 minus 2? 2. So x squared. Negative 15 divided by 3 is negative 5. And then x cubed divided by x squared, again, just subtract them. So that's going to be 1. So that's just going to be x. Okay, because 3 minus 2 is 1. And I don't write the exponent 1 here. It's just understood as 1. And of course, the x squareds go poofy here because x squared divided by x squared is 1 is 1. 21 divided by 3 is 7. So this right here is my final answer. And I'm not going to show you, but if you actually distributed the 3x squared out back through these terms, you would get this. That's how you can check it. I see time and time again students just guessing on what factors. And why? There's literally a methodical way that you can solve it while always getting the right answer. And you can always check to see if you have the right answer. When you distribute it back through, if you do not get that back out, your original question, you did it wrong. That's a great way to check your answer. So I implore you to do that if you're kind of struggling. Like, does it really? Because it helps you trust the math. Okay? Let's go through this one. This one right here is 6x cubed and then minus 6x. So what does this mean? This means I'm still going to look for a greatest common factor. So what is my greatest common factor? Well, I see that there's a 6 in each, so obviously I'm going to have a 6. And then I'm going to take the x. I don't want to take the x cubed because I can't take this 6x divided by x cubed. I get a negative exponent that way. I don't want any negative exponents. Okay? So what I want to do is take the greatest common coefficient, but technically I want to take the least common exponent of my expression. So here I took the squared instead of the fourth. Okay, I took it because obviously it divides into each one evenly. But when you're thinking about the greatest common factor, don't think, oh, the greatest number. It's not that. It's not the greatest common factor is not the greatest number that you see. Okay, so 3 is not the greatest number that you see, so 21. It's the greatest factor that you can take out evenly. That's what it is. The factor is the important part. It's the greatest factor. A factor, again, is two things that multiply together to give me a number. So everything has a factor, at least two of them. 15 has a factor of 5 and 3, but also 15 and 1. 1 has a factor of 1 and 1. 1 times 1 is 1. Okay? 2 has a factor of 2 and 2 factors of 2 and 3. 9 has a factor of 3 and 3, 9 and 1. 100 has 10 and 10. It has 101. It has 20 and 5. And so you can continue over and over. The greatest common factor here is 6x, not 6x cubed. So what this means is I'm going to take 6x, and I'm technically going to divide each one by 6x. This becomes x squared, and this becomes just minus 1. Okay? That becomes minus 1. Now, this is kind of, this right here is kind of a trick question because, yes, it's greatest common factors, but technically you can actually factor this out a little bit more. Okay? Yes, when I distribute it, I can get this out. But this part right here, and we're going to learn what this is in a couple more slides, so stay with me. This right here is what we call perfect squares. Okay? The perfect square. Why is it a perfect square? Or sorry, difference of perfect square. It is a perfect square, but technically it's called the difference of perfect square. The reason why it's a difference is because obviously the minus sign. Okay? Why is it perfect square? Because both of these terms, the x squared and the 1, are perfect squares. That means I can square root them and I get an answer. That's what it means. I can square root x squared and I get x. I can square root 1 and I get 1. So what does this actually equal? This actually equals 6x, and then this breaks down into x plus 1 and then x minus 1. I'm going to show you that in a couple more slides. So this is technically a trick question, so I apologize. But it does break down a little bit more into this, okay? Into that. And again, if you FOIL this out, if you FOIL the x plus 1 and the x minus 1 out, and then you distributed the 6x to that, you would get that. You would get it back. Okay? And then we're going to, let's go through it. I didn't know if I wanted to go through this one or not, but factor completely or state that the polynomial is prime. Now, this one also said if the polynomial is prime. Now, what does that mean? A prime number is a number that has no other factors besides itself and 1. So 17, 19 are perfect prime numbers, 11, because those numbers don't have anything multiplied together to give me that number. I can't multiply any number together to give me 19 or 17. It's just not possible. I can't multiply any number together to give me 11 or even 2, except for its own number, so 2, and 1. 1, so 2 times 1 is 2. But that aside, that means it's still prime. So I don't have like a 3 or a 5 or a 7 that multiplies together to give me 2, right? That's why it's prime. Same thing here. So is there anything in this polynomial here that I can multiply together to give me prime numbers? Or sorry, to give me a factor, to give me something? And the answer is actually no. There's nothing that I can multiply together that gives me this. Nothing that's real. Okay, this is a straight up imaginary example. So this is prime and no real factors. That's what I would say. So this is no real factors. It does have imaginary factors, sure, but no real factors. Okay, so that's greatest common factor. Let's move on. So difference of two squares. We literally just went over this. Perfect squares, difference of two squares. These are sort of perfect squares or difference of two squares. But yeah, they're basically perfect squares, but not exactly how we saw it before in the last example. So when I do this, factor the difference of two squares, I notice that there's, of course, two of them, and there's a difference, and these both must be squares, which means when I square root each of them, what happens is they need to be square rooted evenly. So what is square root of 9? Well, that's 3. Square root of x squared, that's x. What's the square root of 64? That's 8. All right, perfect. So now that I have all of that, what I actually do here is set up the following template. This gets a negative, but then I also have something else that I tag onto it, and it's the positive. That is my factorization. Okay? And if you don't believe me, factor it out. Distribute it out. Not factor, but distribute it out, and you will get this. Okay? The next one is very, very similar. These both need to be square rooted. I know that it's a difference of two squares and a perfect square if I can square root. So square root of 4 is 2. Square root of x squared is x. 49 is 7. Okay. When I do this, that means this must get a minus. And then what I do is just tag on the 2x plus 7 here. And this is my difference of two squares. Trust the math. Okay, trust it. This lesson is very a trustworthy lesson. Like, you need to trust the math on this. Okay? Let's move on to what we call perfect square trinomials. Perfect square trinomials, what are those? Well, you see something like this. Now, perfect square trinomials, I have to notice two things here, and it's this. The reason why it says it's a perfect square is because my first term and my last term are perfect squares, meaning, just like what I said before, I can square root both those terms and I get just a straight up number. Now, when I have something like this, I do basically square root, and I know it's going to be something like x and then 7. But the problem is I need to know what exactly goes in here, and then if I tag on anything else. Well, the fact is you do tag on something else. And that something else is the negatives. The reason why it's negatives, guys, is because if you remember from Algebra 1, if I look right here, this is positive. And since that's positive, I always look at that sign to see if it's negative or if it's positive. If it's negative, that means both of my parentheses when I factor out will be negative. Okay? If this is positive, if that's positive, and then you look at that sign, and that first sign is positive, then they're both going to be positive. Okay? If this sign is negative, no matter what, even if this sign is positive or negative, you will have a negative or positive in either one. Okay? That's review. But that aside, I'm going to get more into that later. This can actually be broken up, or not broken up, but simplified down to x minus 7 squared. That's what it can be simplified down to. X minus 7 squared. Okay? Perfect. So, get it? Perfect square. Ha ha ha. All right, so this is the square root right here. I can square root both of them. What's the square root of 9? It's 3. Square root of x squared is x, and this is 1. Now we look at, see, this is positive, so that means we look here. Oh, that's negative, which means this gets a negative. And then technically this is x minus 1 as well, but that's double, which means this is 3x minus 1 squared. Okay? That's what it means. Perfect. Oh man, that's such a good pun. I love that. That's amazing. All right, the last one here. Factor the perfect square. Exact same thing. Try to do this one by yourself and see what you get. So you should get this. X minus 5 quantity squared, because this is x square root. That's the square root of 5. This is positive. You go with that. Okay, that's negative, which means this gets negative. I have to tag on the other, which equals that. Awesome. That's the perfect square. So let's erase, and let's move on to what we call the factoring trinomials with a leading coefficient of 1. So what if my leading coefficient is 1? My LC is 1. So if this is the case, find two numbers that multiply to the last number and add to the middle number. So multiply to the last number and add to the middle number. That's all you need to do. So we're going to go through these three examples, and let's go to town. Now this is very similar to what we did during the bell work. What are factors that somehow, some way, factors of 32, that somehow, some way add to negative 14? Factors of 32 are 8 and 4. That's definitely one of them, right? Or I can do 16 and 2, or I can do 32 and 2, okay? Now, here, 8 and 4, that does not, no matter what I do, even if they're both negative or positive, it doesn't even get me to 14. Even if I put both of them in negative, it doesn't give me there. It gives me to negative 12. Okay, so I can't do that. But then I can't do 32 and 1 because that's totally not close to 14. But this is close to 14. Now, the problem is which one gets a negative? Well, the negative has to be with the 16 is because if I take negative 16 plus 2, it gives me negative 14. If I take 16 minus 2, if we put the negative with the 2, that would be just 14, positive 14. So I don't want that. I want negative. So how does it break apart? Well, my basic template looks like this. And then I just tag those in. So minus 16 and then plus 2. And then I'm done. Okay, same thing here. I'm going to factors of 72, and the easiest factors are 9 and 8. Now notice how this is a positive, guys, and that is a negative, which means both sets of parentheses are going to be minus. And since these are my factors that add up to 17, this is 9 and this is 8. And then I'm done. That's it. Notice how none of these have equations, by the way. We're expressing that. We're doing expressions. We're simplifying expressions. They're not equations. So when you're doing factoring, guys, I should not be seeing on your homework quizzes like 5. When I say factor this and you put 5, that is completely and utterly wrong. It's basically like if I ask you what time it is and then you say Orlando, Florida. That's equivalent to what you're putting in. I want you to know that. When you're factoring these out, and if you're just like, I got 5, that's equivalent to if I ask you, what time is it? You say Orlando, Florida. They're completely two different things. When I say factor and solve, which we will solve tomorrow, they're two different things. When I factor it, all I'm saying is factor it using the expressions. Okay, but when I say solve, I want to know what x equals. Just like time and place are two different things, right? So keep that in mind, that these are expressions, and you're not going to put like 5 or 7 or like negative 1/2. It doesn't work that way. Here, what are factors of negative 18? Factors of negative 18 are simple, just 9 and 2 and then 6 and 3. But which one is probably going to somehow, some way add up to negative 7? 9 and 2. So go ahead and do this one on your own, and then pause the video and then see if you can get it right. Do it. Do it now, please. Great. That's what you should get. The reason why the negative goes with the 9 is because if I take negative 9 plus 2, it gives me negative 7. But negative 9 times 2 still gives me negative 18. So it checks out, smiley face, and then a unicorn. All right, let's erase and move on. That was with leading coefficients equal to 1, equal to 1. What if I have a leading coefficient equal to not 1? Okay, meaning I have a leading coefficient that is not 1, such as a 2 or 3 or 4. We're going to be using the method of what I call the divide and slide method. That's what I'm going to call it. It's called the divide and slide method. Okay, so what if I have something like this? Now notice in the previous examples, we didn't have a number attached here. But now that we have a number here, what are we going to do? Okay, we're going to freak out? No, we're not going to freak out. What we're going to do is follow the example of my divide and slide. So my first step is to take the 3 times the negative 28. So take the 3 times the negative 28. So I'm going to do that off to the side. This gives me negative 84. Now, what I want to do is find factors of negative 84 that somehow, some way add up to 40. This one's a little bit harder. What two numbers multiply to give me negative 84? And so you kind of have to play around with the calculator a bit, but it's not too hard to find because I know it's even, so it has to be divisible by an even number. And you could try 2, and if you did 2, then you would be correct. You would get 42 and 2. 42 times 2 gives me 84. Now, which one gets the negative? Okay. If this is a positive, that means a bigger number needs to be the positive number, which means the 2 needs to be negative. So that means my second step is to say y, and then minus 2, and then y plus 42. Okay, that's what it is. And the divide and slide problem says this, and this is the third and most important step. I now take my leading coefficient, which is 3, and now what I'm going to do is divide by that number, divide by those factors. And the rule says if it doesn't divide, you slide. Okay, if it doesn't divide, you slide, which means look at this negative 2 all over 3. Does that divide? No, it doesn't divide, which means I slide it over. Okay, so this final answer is 3y minus 2. No guess and check at all. I don't know if you remember in Algebra 1 when you took it, maybe a lot of you did guess and check. You don't need to guess and check at all with this method. It works every single time. Okay, now this 42 divided by 3, is that an even number? It actually is. It is 14, which means this is my final answer. No guess and check at all. Okay, let's do another one of these. So same thing, I'm going to take 5 times negative 28. So 5, my first step, 5 times negative 28. This equals negative 140. What are factors of negative 140? Think about it. To somehow, some way add up to 4. Think about the easiest ones. You should be thinking of 14 and 10. Okay, 14 times 10 gives me 4. 14 times 10 somehow gives me 4. How does it give me negative 4? Well, the negative needs to be with the 14. So my second step is to take my a minus 14, and then a, and then plus 10. Now what I do is divide by my leading coefficient, which is 5. Okay, so I divide by 5, divide by 5. Now the rule says if it doesn't divide, you slide. Does this divide unevenly? No. 14 is not divisible by 5, so that means I take 5a minus 14 to be my first one. And then does 10 divided by 5? Yes, it does. So that means a plus 2. This is my final answer. Awesome. So go ahead and try the third one here. See if you can do it yourself. Pause the video, really try it so you can test yourself and see if you can get it correct. Perfect. This is what you should get. So if you got something similar to that, great job. If you actually got that, fantastic. Okay? We are now going to move on to some of the harder, more advanced algebraic factoring, and that is sum of cubes and difference of cubes. Okay, so this is my actual, right there, that's my actual formula. It looks pretty scary, but it's actually not. And I'm going to go through probably just one of these examples for the sake of time because I don't want to take up too much time, guys. So I'm only going to probably go through one of these. And in this case, I'm probably just going to go through, let's just go through this one, the first one, okay? So what will this mean? When I factor this, the sum of cubes, a good acronym to know this is called SOAP. So when you're looking at the sum of cubes, okay, because it's cubes here, cubes for my exponents. SOAP means same sign, opposite sign, and then always positive. So same sign, that's plus, opposite sign, minus, and then always positive. So SOAP is a good acronym there to help you know that. First thing I need to do is understand what my A value is here. and then also what my b value would be. Now this one's a little bit tricky because it does have an a value in here, but most of the time when I just cube root, if I cube root both of these, this would be my a value. If I cube root this, then a equals a, which is not bad. And then if I cube root 64, that gives me 4. So now that I have these two values, I really just plug them into my formula, and that's literally it. So what I have is a plus b. So what's my a? Well, a equals a. So a plus b, which is 4, times a squared. So take a. So I take a squared minus a times b. Well, a times b would be 4a. So these two numbers together, 4a. And then b squared, what's 4 squared? Is just 16. And that is how I would do my my sum of cubes. My sum of cubes here. We're going to go through the difference of cubes, at least one example there. And it's literally the exact same thing, just with different signs and its difference, okay? So if that wasn't too hard, that's amazing, awesome. That makes me happy inside. Okay, let's continue on, and I'm going to do one example for what we call difference of cubes. Now these can get a little bit more complicated, but they don't need to be complicated. So I'm not going to do this one, and I'm not going to do this one. Let's go ahead and do this one together. This one's a little bit complicated because it has two kind of variables in here, but the basic thing is I still want to cube these. So what is going to be my a? Because again, guys, this is my formula, right? So what's my a? What's my b? Well, my a right here is usually the first term. So I cube root that. That goes poofy. So I'm left with just x. And my b here, when I cube root this, I have two things that are going to be given to me. If I cube root 8, I get 2. But if I also cube root s cubed, based on inverse properties that we learned last week, I get just s. So that's my b value, and that's why it kind of gets a little bit tricky. So let's start plugging everything in. So my a, following my formula, a minus b. Notice how this is still same opposite sign and always positive for SOAP. Helps you kind of remember it, right? So same sign for minus minus, so a minus b. So this is x minus 2s times a squared, so x squared, and then plus a times b. So this is actually plus 2 times xs. Okay, I can just multiply them all together. And then this is going to be plus. Now when I square this, I'm going to put this in red here. I'm going to square my b value. What that means is that I'm going to take 2 squared times s squared, which gives me 2 squared is 4, s squared is just s squared. I need to transfer that 2, that squared terms, in both of those things. That's what makes this one tricky, just the 2 out front. Okay? And that is it. I'm done. So now I can finish my parentheses. And that is my final answer. Very similar to sum of cubes. I understand that. So really the hardest thing is sometimes you'll get this, like the 2s, and then really just recognizing the formula, like the minus, the positive, where they go. Okay? But that's the only one I'm going to go there, just for the sake of time. Now, I'm going to go through these really quickly, and then the last slide, I'm really just going to go through each one, and I want you to try it out. I want you to actually test yourself out. So I'm not really going to explain the math. I'm just going to show you the answers. But here's a general strategy, an outline, if you will, in factoring these completely. If I ask you, and the next slide will ask you, factor something completely. When it says factor something completely, what you're going to be using are these basic steps or outline. First of all, you're always going to ask, is there a GCF? You must always ask if there's a GCF. You have to ask that. Secondly, you have to ask if it's a binomial, meaning is it a difference of squares? Okay? So is it like x squared minus 16? That's a difference of perfect squares, and that's a binomial. Is it a trinomial? And if it is it a perfect square trinomial? Is it the leading coefficient equal to 1? And is it not equal to 1? You have to kind of go through these logical steps, okay? And then keep factoring until it is factored completely. So the first thing is always the GCF. So make sure if you need to get this down, pause the video and get it down. So I'm going to just show these to you, and I'm just going to go through each one by one and show you the answer and which one, how to factor each one completely, okay? So this first one, try it yourself. See if you can factor this completely. It's a little tricky with the fourth there, actually the fourth, but we can do it. Okay, so this is the answer for this one. The reason why it's tricky is because it's the fourth power, but all I have to do is still square root both sides. When I square root both sides, I mean, if I square root the x to the fourth, I get x squared. Okay, and since it's this, I can square root both sides. This is actually a difference of squares, but you can also factor it more. So that's where I started with. It's a difference of squares because it's a binomial. And since it's a difference of squares, I do the square root. And so the square root of x to the fourth is x squared. And then, of course, the square root of 256 is 16. Because it's a difference of squares, I need to have a minus and a positive. Then I notice that this is actually breaking down into another difference of squares. Okay, sorry, this should be a positive right there. This should be breaking down in another difference of squares. So x minus 4 and x plus 4, because I can square root this even more. Okay, so that one's tricky just because you can continue, keep going, keep going, keep going. All right, go ahead and try this top one up there, and then we'll see what we get. With this one, the GCF is 5. Now notice I do have a GCF in this question, in this problem right here, because each one is divisible by 5. In this one, I didn't have that. Okay, so since I didn't have that, I can't just, do that essentially. I can't divide anything by 5 here. But here I can. So I took it out of the 5. And then what I notice here is I can still factor that into, because it's a trinomial, it doesn't have any more GCF, but factors of 42 that somehow, some way add up to -1, that's going to be 7 and 6. And since it's -1, the negative gets with the 7. Okay? One last one, and then we'll be done. Try this bottom one here. This one is, again, tricky because it's sort of kind of combining both of the top questions. You do have a GCF. Your GCF is your y squared, so you always should take that out. And once you take that out, you notice that this is actually a difference of squares right here. And so since you have a difference of squares, 25 squared is 625, so the square root of 625 is 25. Square root of y to the fourth is y squared. But then you also notice this is another difference of squares. And so you square root both of those terms to get these, okay? And then that's the final completed answer. Remember, this right here is prime, so you can't do anything more. Same thing with that plus 16. There's no real factor that can do that. There is imaginary factors, but we're not going to get into that, okay? Fantastic. So that is the whole of the lesson. That is factoring. What we learned was the greatest common factor of the polynomial expression. We learned how to factor trinomials with leading coefficient equal to 1 and the leading coefficient not equal to 1. We learned how to factor difference of two squares with the perfect squares, sum and difference of two cubes, and then also to factor completely. Okay, the homework quiz, of course, is going to be optional now during this online learning. But if you have any other questions, just please be sure to email me and let me know. The homework is, of course, on Math Excel. This is C Squared Mathematics. Be sure to like and subscribe. Peace out and make good choices.